Okay, hello. My name is Emily. Thank you for having me, the organizers. This is a wonderful place. The minute I arrived here, I was like, this looks straight out of a German fairy tale. Not what you see in America. Right, like many other participants in the audience, I'm also extremely jet-lagged, so I hope that you can at least digest some of what I'm about to talk to you about today. Okay, so I won't go too deep into the introduction because Lou gave a very nice contextualization of the work that I'm going to talk about today, which is going to be thermal Hall for Mott insulators. And it's one of the most powerful probes for insulating systems because it tells you the information about the underlying excitations that can carry heat in different ways, and specifically the way that the mechanism behind which these heat carriers can carry heat, it depends on the underlying type of heat carrier. So we have phonons, magnons, and if you want to get fancy, you have spinons and fractionalized excitations. They all carry heat in different ways. Okay, so one thing that we've heard a lot about today is the phonon thermal Hall transport. And specifically, our work is going to be motivated by these experiments where they measured large thermal Hall conductivity in the undoped cuprates, so the parent compounds of the cuprate superconductors, and these has been attributed to phonons. And another thing that we heard a lot about today is the fact that phonons can carry heat in, or contribute to the thermal Hall effect in two main ways. The first way is the intrinsic thermal Hall effect, which includes the phonons having a barrier curvature themselves, or that they also couple to topological quasi-particles such as magnons that also can contribute to phonon thermal Hall. And then the other mechanism is extrinsic mechanisms, which, as mentioned, scattering off of impurities and domain boundaries. But on the theory side, these phonon thermal Hall, I mean, other than the talk that Stephen just mentioned for alpha ruthenium trichloride, the mechanisms applied to the cuprates, the phonon thermal Hall magnitudes cannot reproduce the magnitude of the values seen in an experiment. And so that motivates us to explore other mechanisms, like what else can generate thermal Hall in these square lattice cuprate compounds. And so we consider something that we all have talked about at this conference is magnon thermal Hall transport. And you can get magnon thermal Hall generically in systems that break SU2 symmetry. So for example, if you have a cation interaction or a DM interaction, then it typically can give rise to a thermal Hall effect. However, we've also heard about this no-go theorem, such that on a square lattice, if you don't actually break any of these SU2 symmetries, the magnon Hall effect is impossible for spin rotationally symmetric systems. However, this has a couple of caveats. So this assumption was derived based on linear spin wave theory, and they do not consider non-interacting magnons. And as some speakers pointed out yesterday, magnon interactions are very important. And moreover, they don't consider any scattering effects. And another thing they don't consider is that they only really consider the minimum chiral coupling or DM coupling. They don't really consider higher order exchange terms that might become important when you have a Coulomb interaction U that's near to the Mott transition. So these higher order spin fluctuations that's mediated by the charge is not considered. Okay, so our question is, what are the requirements for observing intrinsic thermal Hall effect? And here, by intrinsic, I mean no phonons, no disorder, in Mott insulators. Okay, so my claim, which I hope to convince you of today, is that you need to break both particle hole and time reversal symmetry to see a finite thermal Hall effect. And I hope to convince you of this in three ways. First, I'm going to provide a symmetry argument that shows that you don't see a thermal Hall effect when your system has particle hole symmetry and or time reversal symmetry. And That's nice, but symmetry arguments don't give us magnitudes. It just says that generically the inverse here is possible. So if you break particle hole and you break time reversal symmetry, you can generically generate a finite thermal Hall, but it could be 10 to the minus 5, it could be 0.1. You really need to do numerical simulations to tell you about how large this magnitude is. So we do this using extensive DQMC simulations, so that's determinantal quantum Monte Carlo. And we see that for our lowest temperature, the thermal Hall conductivity is on the order of around 0.01 to 0.1 kb squared over h bar. And finally, why do we see this? What gets us around the no-go theorem here? And so we explore one possible mechanism that is essentially magnon-magnon scattering. And so we provide a qualitative argument to why we see something finite in our numerical studies. Okay, so first things first, let's go to the symmetry argument. So we consider a Hubbard model, essentially with near neighbor and next nearest neighbor hopping. And we also consider an out-of-plane field that comes through in this complex hopping amplitude. And the presence of a T prime breaks charge conjugation, or particle hole symmetry, and the presence of a magnetic field breaks time reversal symmetry. And so the first constraint that we have to obey is the Onsager-Casimir relations, which essentially says that if you change the direction of your magnetic field, then your thermal Hall has to be odd. And you can show that if your Hamiltonian is particle hole symmetric, then the thermal Hall conductivity is even under a change in the field. And it's a very short derivation to show this. And so the following is, if both 1 and 2 are true, then kappa xy must be 0. And so the inverse condition is also true. So if your Hamiltonian breaks particle hole symmetry, you're no longer constrained by constraint 2. And so you can generically have a finite thermal Hall conductivity. OK, so now let's move on to the numerical simulations. So what we do is determinantal quantum Monte Carlo, and this directly simulates the Hubbard model, and it is a non-perturbative approach. And I won't get too much into the details of what this method does, but if you're interested in how DQMC actually works, you can talk to me after. But essentially what DQMC measures is unequal time correlators. And we can use these unequal time correlators to calculate the heat-current correlator in imaginary time. But that's bad because we don't want to be in imaginary time. We want to be in real time. And so we have to perform a numerical analytic continuation. And we do this using a maximum entropy algorithm. And using the max-n algorithm and having our, in order to calculate these correlators, we then plug it into the usual Kubo formula to calculate the transport coefficients. And so you may ask, how do we trust these results? Analytical continuation is an under-constrained problem. And you would be right to question those results. So to give us confidence in what we're seeing is actually right, we look at a proxy that doesn't depend on analytic continuation that states that the thermal Hall conductivity should go like the Hall number times kappa xx squared. And so the proxy and the analytical continuation should agree at least at lower temperatures. OK, so the first of our DQMC results. Here I show the longitudinal optical conductivities. So on the left, we have the electrical conductivity as a function of omega. And then on the right, we have the thermal longitudinal conductivity as a function of omega. And what we see is that as you decrease the temperature, then the electrical conductivity actually gaps out at low temperature. Whereas the thermal DC conductivity is finite. So that tells us that we have an electrical insulator and a heat conductor. And so that's how we know that we're actually in the insulating regime. And to further support this, we can also calculate the specific heat. And at all values of T prime that we use, you would expect two peaks in the specific heat. One at high temperatures corresponding on the scale of the Coulomb interaction U, where you have a crossover between where you're projecting out the doubly occupied states as you cross over to the lower temperature. And then you have this lower peak in the specific heat where you are crossing over from a fermionic charge transport regime to a magnon transport regime. And this occurs on the order of the exchange J. Right, and so here's the money plot. And from left to right, we have the thermal Hall number, the thermal Hall angle, and the thermal Hall conductivity. And the plots are of increasing T primes, and the solid plot is the proxy, and the dotted lines are the analytic continuation results. And you can see that they qualitatively track each other, especially at lower temperature. And so, right, so the proxy and the analytical continuation methods qualitatively agree, which gives us confidence that our results are meaningful. Moreover, the thermal conductivity increases with increasing T prime, and T prime, as discussed before, controls the degree of particle hole symmetry breaking. And moreover, at low temperature, at T is less than J, where we go into the magnon transport regime, we have a finite thermal Hall, and this violates the no-go theorem result derived using linear spin wave theory. Okay, so how do we get around the no-go theorem? So we explored a possible mechanism, which is magnon-magnon scattering. And if you do a strong coupling limit expansion, so strong U expansion, you project out all of the doubly occupied and empty states, and you get an effective Hamiltonian at the lowest order, which is J1, J2, and J chi. And notice here that J chi is actually dependent on the square lattice of T prime and B. So if you don't have particle hole symmetry breaking and time reversal symmetry breaking in your parent Hamiltonian, then J chi does not appear. And we can do the usual Holstein-Primakov transformation and Bogoliubov transformation here because we have two species of magnons. And you can write down a quadratic magnon Hamiltonian, which I think most people here are familiar with, as well as this quartic term. And alpha and beta are species of the Bogoliubov quasiparticles. And the size here are just different combinations of alpha, alpha dagger, beta, beta dagger. And you see that the interaction term has two types of vertices. So the first type is purely real, which is proportional to the J1 and J2 in higher orders of linear spin wave theory, up to 1 over S. And the second type is purely imaginary, which is proportional to S times J chi. And this is heavily, heavily inspired, and the formalism used by Alex and his student. And these are heroic calculations where they calculated the Boltzmann transport for a different system, ferromagnet. And you can essentially relate the thermal Hall conductivity to the rate of magnon mode collisions. I attempted to do this. I got halfway through, and then I immediately gave up because the amount of diagrams that you have to sum over is insurmountable. But my goal is not to show a quantitative comparison, but more like a qualitative explanation as to one possible mechanism that gives rise to magnon thermal Hall. So to calculate these magnon mode collisions, you can use Fermi's golden rule, and you can generate the terms that contribute to the scattering at second order perturbation theory are terms mediated by J chi, J chi, J chi, J1, and J1, J1, and other types of terms. But what you see is that only the collisions mediated by the J chi interaction contribute to the off-diagonal scattering. And so you need J chi in order to generate a finite thermal Hall effect in this mechanism. And you can write down the form of kappa xy. This is very, proportional. Like there's tons of form factors and complicated things in front that I'm omitting here. But again, qualitative statement is that kappa xy to leading order can give you something that's linear in T prime. and B at small fields, which is consistent with our DQMC results. Okay, so in summary, I think I talked really fast, but the TT prime U Hubbard model on the square lattice exhibits a non-zero thermal Hall effect under an applied magnetic field. And the takeaway is that one should not naively ignore potential magnon contributions based on the no-go theorem, which has a much narrower regime of validity than commonly interpreted in experiments. Thank you.